Hello everyone, I am Dr. Lakhvinder Kaur, Associate Professor at Rungta College of Engineering and Technology, Bhilai. Today I am going to explain a topic overview of optical fiber communication. I hope to share some valuable insights that will benefit you all. So let's get started. These are the outline of presentation which we are going to discuss in this lecture. Optical fiber communication system. What is optical fiber? Evolution of optical fibers, structure of an optical fiber, different types of optical fiber cables, optical fiber communication system components and key components of fiber optic system. Optical fiber communication system. Optical fiber communication system is a way for transmitting information from one place to another. The information may be in the form of voice, data, message, etc. In fiber optics, information is coded in a beam of light and sent down a glass or plastic pipes. These pipes are called as optical fibers. Now, what is optical fiber? An optical fiber is a thin, flexible, transparent fiber made by glass or plastic to a diameter comparable with the human hair. Optical fibers are used most often as a means to transmit light between the two ends of the fiber. A fiber optic cable can have a few as 2 strands or as many as several hundreds. Each strand can carry something like 15,000 telephone calls. So, an entire fiber optic cable can easily carry several million calls. Now, the evolution and the history of optical fiber. Starting with the conceptual beginning, the idea of using light for communication traces back to the late 19th century with early experiment in guiding light through bent glass rods. First optical fiber in 1970, Corning Glass Works produced the first optical fiber with a loss of 20 dB per kilometer, which was a significant improvement over earlier attempts. Milestones in transmission. By the mid of 1970, practical optical fiber cables capable of transmitting signal over long distance were developed and deployed. Deployment in telecommunication. Throughout the 1980s, optical fiber technology matured and became the standard for the telecommunication networks, replacing copper wires due to its superior capacity and reliability. Advancement in transmission. The development of erbium doped fiber amplifiers in the mid of 1980s allowed for long distance transmission without frequent signal regeneration, further boosting the efficiency of fiber optic networks. Widespread adoption. From the year 1990s onwards, fiber optics became important in global telecommunication networks, providing the backbone for internet infrastructure and high-speed data transmission. Continued technical advancement. Advancements such as wavelength division multiplexing in year 1990 and dense wavelength division multiplexing in the early of 2000 dramatically increased the capacity of optical fiber systems, allowing multiple channels of data to be transmitted simultaneously over a single fiber. Research and development. Ongoing research continues to improve fiber optic technology, including the development of new type of fibers such as dispersion shifted and non-zero dispersion shifted fibers and more efficient signal processing techniques. Now, let us discuss the structure of an optical fiber. Optical fiber cable consists of 4 parts, namely core, cladding, buffer, jacket. The core of a fiber cable is a cylinder of plastic that runs all along the fiber cable's length and offers protection by cladding. The diameter of core depends on the application used. due to internal reflection, the light travelling within the core reflects from the core the cladding boundary. The core cross section need to be circular one for most of the applications. Cladding is an outer optical material that protects the core. The main function of the cladding is that it reflects the light back into the core. When light enters through the core into the cladding, it changes its angle and then reflects back to the core. The main function of buffer is to protect the fiber from damage, and thousands of optical fibers arranged in hundreds of optical cables. These bundles are protected by the cable's outer covering, which is known as jacket. Fiber optic cables jackets are available in different colors that can easily make us recognize the exact color of the cable we are dealing with. The color yellow clearly signifies a single mode cable, whereas yellow-orange color indicates the multimode. Total internal reflection: if the light hits the interface of any angle larger than its critical angle, it will not pass through to the second medium at all. Instead, all of it will be reflected back into the first medium. This process is known as total internal reflection. Now, how light travels inside a fiber? Light travels through optical fiber based on the principle of total internal reflection. Optical fibers are designed to guide light efficiently from one end to the other, often over long distance. A hair-thin fiber consists of two concentric layers of high purity silica glass, the core and the cladding, which are enclosed by a protective shield. Core and cladding have different refractive indices, with the core having a refractive index N1, which is slightly higher than that of the cladding N2. It is this difference in refractive index that enables the fiber to guide the light. Because of this guiding property, the fiber is also referred to as optical waveguide. Different types of fibers. Based on fibers used in communication, they are classified into four categories. First is step index fiber. It has a core with a uniform refractive index and a cladding with a lower refractive index. Light travels straight down the core, but different modes travel at the different speeds. The refractive index of core is higher than that of the cladding, but it suddenly changes at the core cladding interface. These fibers are classified into two types based on number of modes they can transmit, and they are single mode step index fibers and multi-mode step index fibers, less commonly used in modern application due to higher model dispersion. Second type of fiber is graded index fiber. Refractive index of the core decreases gradually from the center outward, allows multiple modes of light to travel more efficiently than step index fibers. It reduces modal dispersion, improving the bandwidth and performance. Graded index fibers are type of optical fiber where the refractive index of the core gradually decreases from the center to the edge of the core. This gradual decrease in refractive index helps to reduce modal dispersion, allowing for fast and more efficient data transmission. The index profile is typically parabolic or near parabolic in shape. Graded index fiber have several advantages, including reduced modal dispersion, increased bandwidth, longer distance transmission and easier splicing. They are commonly used in local area networks, LANs, metropolitan area networks, MANs, data centers, high-speed internet connections. Graded index fiber offer a compromise between single mode and multi-mode fibers, providing a balance between bandwidth and distance capabilities. Third type of fiber is single mode fiber. Single mode fiber is a type of optical fiber that is designed to transmit a single beam of light over long distance. It has a smaller core diameter, typically 10 to 12 microns, and a higher bandwidth than multimode fibers, allowing for fast data transmission rates and longer distance transmission without signal degradation. Single mode fiber is commonly used in telecommunication, for long haul networks, internet backbone and cable TVs. Data centers for high speed data transmission between servers and storage systems. Similarly, metro networks for connecting buildings and campuses. Access network for fiber to the home and fiber to the premises applications. Single mode fiber has several benefits, including higher bandwidth and faster data transfer rate, longer distance transmission without signal repeaters, lower attenuation and interface, smaller diameter and lighter weight. However, single mode fiber also has some limitations, including more expensive than multimode fibers, requires precise alignment and splicing, not suitable for short distance application due to its higher cost and complexity. Fourth type of fiber is multi-mode fibers. Multi-mode fibers is a type of optical fiber that can transmit multiple beams of light over short distances. It has a larger core diameter, typically 50 to 100 microns, and a lower bandwidth than single mode fibers, but is more cost effective and easier to install. Multimode fiber is commonly used in local area networks for connecting devices within a building or a campus. Secondly, metropolitan area networks for connecting buildings and campuses within a city. Third, data centers for short distance data transfer between servers and storage system. Fourth, industrial control system for monitoring and controlling industrial equipments. Fifth and most important, security system for video surveillance and access control. Multimode fiber has several benefits, including lower cost and easier installation, shorter distance transmission without signal repeaters, easier to splice and connect, supports multiple signal transmissions simultaneously. However, multimode fiber also has some limitations, including lower bandwidth and slower data transfer rate, shorter distance transmission, typically up to around 10 kilometers only, more susceptible to interference and signal degradation. There are two main types of multimode fibers. First, step index multimode fiber. It has a constant refractive index in the core. And second is graded index multimode fiber. It has a gradually decreasing refractive index in the core, allowing for faster signal transmission. Now, let us discuss the fiber optic communication system. An optical fiber communication system is a system that uses light to transmit information over long distance through optical fibers. The basic operating principle of a fiber optic communication system involves few components. First component is signal generation. The transmitter generates an optical signal by modulating a light source with the information to be transmitted. Second is transmission. The modulated light travels through the optical fiber. The light pulses present the transmitted data. Third is amplification. Optical amplifiers boost the signal strength to counteract attenuation over long distance. Next is reception. The receiver captures the optical signal and converts it back into the electrical signal using a photodetectors. Last component is demodulation and processing. The received signal is modulated to retrieve the original information. So, let us discuss all the key components of optical fiber communication system in detail. Let us start with the optical transmitters. Optical transmitters, they convert electrical signal into optical signal for transmission through optical fibers. The key elements of optical transmitters are light source like laser diodes. It provides coherent light with high intensity and narrow spectral width, commonly used in long distance and high speed application. Light emitting diode, it emits incoherent light with broader spectral width and lower intensity, used in short distance and lower speed application. Second component is modulator. Direct modulation, the electrical signal directly modulates the current driving the light source, causing the light intensity to vary in accordance with the signal. External modulation, the light source operates continuously and the light is modulated externally using devices such as electro-optic modulators or acoustic optic modulators. This method is used to avoid chirp and maintain signal integrity over long distance. Third component is driver circuit. It converts the input electrical signal into a suitable format to drive the light source. It ensures the correct amplitude and timing for the light modulation. Next is wavelength stabilization. It ensures the emitted light maintains a stable wavelength, crucial for wavelength division multiplexing system. This can be achieved by using temperature control and feedback mechanism. Optical coupling efficiently couples the modulated light into the optical fiber with minimal loss. This optical involves lenses, mirrors and fiber pigtails. Different types of optical transmitters. First is light emitting diodes, LEDs. LEDs are commonly used in short range optical communication systems such as within buildings or for local area networks LANs. They emit light when current flows through them, producing incoherent light in the visible or near infrared spectrum. LED transmitters are simpler and less expensive than laser based transmitters, but typically have lower bandwidth and transmission capabilities. Next element is semiconductor lasers. Semiconductor lasers such as Fibre Optic lasers, distributed feedback lasers, vertical cavity surface emitting lasers are widely used in long distance optical communication system. They emit coherent light with a narrow spectral width, allowing for higher data rates and longer transmission distances compared to LEDs. Next is optical receivers. Optical receivers are essential components in an optical fiber communication system. These are responsible for converting the incoming optical signal back into the electrical signal. The key elements of optical receivers are photodetectors. First type of photodetector which is used as an optical receiver is pin diode, a type of photodiode with an intrinsic layer between the p-type and the n-type semiconductor layer. It converts light into electrical current and is widely used due to its simplicity and cost effectiveness. Second type of photodetector is avalanche photodiode, a photodiode that operates with high reverse based voltage leading to internal gain through impact ionization. It provides higher sensitivity and is used in applications requiring detection of weak signals. Next component is preamplifier. It amplifies the small electrical signal generated by the photodetectors. It typically includes a low noise amplifier to maintain the signal to noise ratio. Next is equalizer. It compensates for signal distortion and attenuation that may have occurred during the transmission through the optical fiber. This helps in restoring the original signal shape. Demodulators. It extracts the original information from the received signal, especially in cases where advanced modulation techniques are used. Signal processor performs the various signal processing functions such as error detection, correction, filtering and clock recovery. This ensures the integrity and accuracy of the received data. Now, different types of optical receivers. First is direct detection receiver. The most common type where the photodetectors directly convert the incoming light into an electrical signal without the need for additional optical components. Simple and cost effective, suitable for most standard communication systems. Second type of optical receiver is coherent detection receivers. It uses a local oscillator laser to mix with the incoming signal before detection, allowing the extraction of amplitude, phase and polarization information. This type of receiver offers higher sensitivity and spectral efficiency, making it suitable for high capacity and high distance communication system. Next component is optical amplifiers. Optical amplifiers play a crucial role in optical communication system by amplifying light signals directly without the need of first convert them to electrical signal. This functionality is essential for long distance fiber optic communication. Here are the key functions of optical amplifiers. First is signal amplification. Optical amplification or amplifier boost the strength of optical signals to compensate for signal loss due to attenuation and dispersion over long distances in optical fiber cables. This allows the signal to travel further without degradation. Next component is extended transmission distance. By placing optical amplifiers at regular intervals along the transmission path, the reach of optical communication system can be significantly extended, allowing for long haul transmission without the need of regeneration of the signal. Wavelength division multiplexing capability. Optical fibers can simultaneously amplify multiple wavelengths of light, that is channels, in a wavelength division multiplexing system. This capability is essential for modern high capacity networks that rely on wavelength division multiplexing to increase the bandwidth and efficiency of the optical fiber. Inline amplification. Optical fibers are used as inline amplifiers placed periodically along the fiber route to maintain signal strength. This is critical in undersea and terrestrial long haul communication link. Booster amplifiers. These amplifiers are placed immediately after the optical transmitter to increase the signal power before it enters the transmission fiber, ensuring the signal is strong enough to withstand losses in the fiber. Preamplifiers. These are located just before the optical receivers. Preamplifiers boost the weaken incoming signal to a level that can be efficiently detected and processed by the receivers. Power efficiency. Optical amplifiers improves the overall power efficiency of the communication system by reducing the need of repeated electrical to optical and optical to electrical conversion, which are power intensive process. Reduction of bit error rate. By amplifying the signal and maintaining a high signal to noise ratio, optical amplifiers help in reducing the bit error rate, ensuring reliable and high quality communication. Simplified network design. The use of optical amplifiers simplifies the design of optical networks by reducing the number of repeaters and regenerators needed, leading to lower maintenance and optical cost. Types of optical amplifiers. First is embryum doped fiber amplifier. It uses a length of optical fiber doped with the rare earth element called erbium. Pump lasers at specific wavelength excite the erbium ion in the filter fiber, which then amplify light signal passing through the fiber at wavelength around 1550 nanometers. These are widely used in long haul and metropolitan area networks due to their high gain, low noise and ability to amplify multiple wavelengths simultaneously in the C band and L band. Second type of amplifier is Raman amplifier. It utilizes the Raman scattering effect in optical fibers to amplify the signal. A pump laser injects light at a wavelength shorter than the signal wavelength. The interaction between the pump light and the signal light amplifies the signal through the Raman scattering process, and its applications can be used to extend the amplification bandwidth beyond the capabilities of EDFAs and are often used in combination with EDFAs for extended reach and bandwidth. Next is semiconductor optical amplifiers. It uses optical semiconductor materials similar to those in laser diodes. The signal is amplified by passing through a semiconductor gain medium that is electrically pumped. It is suitable for use in metro networks, access networks and optical switches due to their compact size, integrability with other semiconductor devices and ability to amplify a wide range of wavelengths. Next type of amplifier is thulium doped fiber amplifiers. Similar to EDFAs, but thus it uses thulium ions as the dopant. Amplifies signal in the S band and sometimes in the extended L bands. It is used for extending the usable wavelength range of optical communication systems. Next is wavelength division multiplexing. Wavelength division multiplexing is a technology used in fiber optic communication to combine multiple signals in a single optical fiber by using different wavelengths or colors of laser light. Basic block diagram of wavelength division multiplexing consists of following sections: multiple lasers, multiplexers, optical fibers, optical amplifiers, demultiplexer, photodetectors or receivers. Fiber loss or signal attenuation. Attenuation is a measure of decay of signal strength or loss of light power that occurs as light pulses propagate through the length of the fiber. It helps to determine the maximum transmission distance between a transmitter and a receiver. Losses responsible for attenuation in optical fibers are material absorption, material scattering, fiber coupling losses. Losses vary greatly depending upon the type of fiber used. Plastic fiber may have losses of several hundred dBs per kilometer. Multimode glass fiber has a loss of about 2 to 4 dB per kilometer. Single mode fiber has a loss of 0.4 dB per kilometer or even less. Fiber coupling, splices and connectors. Coupling the fibers to sources and detectors create losses, especially when it involves mismatch in the size of the optical fiber. When it comes to coupling optical fiber, there are two primary methods, splicing and using connectors. So, first method is fiber splicing. Fiber splicing involves permanently joining two optical fiber end to end, and there are two main types of splicing. First is fusion splicing. The end of the two fibers are precisely aligned and then fused together using an electric arc. These are used in situation where a permanent low loss connection is needed, such as in long haul telecommunication and high speed networks. Second type of splicing method is mechanical splicing. The end of the fibers are aligned and held together by a mechanical mixture with an index matching gel or adhesive. These are used for temporary repair or in situation where splicing need to be performed quickly and with low cost. Next is fiber connectors. Fiber connectors are used to join two fibers in a manner that allow them to be easily connected and disconnected. There are various types of connectors, each with the specific design and use case. Key aspects includes the type of connectors. First is subscriber connector. It's a push-pull design widely used in the data communication and telecommunication applications. Next is lucent net connector, smaller form factor, often used in high density connections. Straight tip, band style, used in both short and long distance applications. Ferrule connector, threaded design, provides a secure connection often used in high vibration environment. Multi-fiber push-on connectors, high density connectors that can connect multiple fibers simultaneously, commonly used in data centers. Next is coupling losses. Coupling losses refer to the reduction in optical power that occurs when light is transferred from one optical component to another, such as from a light source to an optical fiber, between two optical fibers, or from an optical fiber to photodetectors. These losses can significantly affect the efficiency and performance of optical communication system. Here are some key points regarding coupling losses. First is misalignment. If the optical fiber or components are not perfectly aligned, part of the light will not enter the receiving fiber, leading to the losses. Misalignment can be angular, lateral or longitudinal. Fresnel reflection. When light passes from one medium to another with a different refractive index, a portion of the light is reflected back. This reflection causes a loss in the transmitted light intensity. Next is numerical aperture mismatch. If the numerical aperture of the two optical fibers or components are not matched, then not all the light entering the receiving fiber will be guided through it. The numerical aperture determines the range of angle over which the system can accept or emit light. Connector losses. Connectors used to join optical fibers can introduce losses due to imperfection in the connector surface, misalignment or dirt and dust on the connector's end faces. Losses result from axial or angular misalignment, air gaps between the fibers, rough surface at the end of the fibers. Here are some advantages over conventional cables. First is wide bandwidth. Low loss in a coaxial cable losses increases with frequency. The higher the frequency of information signal, the greater the loss. Whereas in an optical fiber, the attenuation is independent of frequency. They offer a loss of 0.2 dB per kilometer. Non-conductivity. Optical fibers are non-conductive and also doesn't attract lightning as a copper cable can do. These are usable in explosive environment. Security, it does not radiate signal and is impossible to tap without your knowledge because the system will fail if it is tapped due to the fact that it will leak light. Safety, fiber is dielectric and does not carry electricity. It presents no spark or fire hazard. It does not cause explosion which occur due to faulty copper cable. Disadvantages of fiber optic over copper cables. Optical fiber is more expensive per meter than copper. Conclusion. The fiber optic communication industry is an ever evolving one. The growth experienced by the industry has been enormous and there is still much work to be done to support the need for faster data rates, advanced switching techniques and more intelligent network architectures that can automatically change in response to traffic patterns and at the same time be cost effective. The trend is expected to continue in the future, leading to a new generation in fiber optic communication. Thank you.